Hello and welcome to the first video of my ACSL Prep Guide. In this video, we're going to be covering computer number systems. You've probably used our normal number system your entire life. We have the digits 0 through 9, and once we run out of digits, we move over one place. So for example, after 9 comes 10, and after 99 comes 100. But here's the weird part. Computers don't primarily work with numbers this way. Instead, computers represent information using binary, which has only two digits, 0 and 1. And ACSL takes this a step further. You're expected to understand four major number systems: binary, which is in base 2, octal, which is in base 8, decimal, which is in base 10 and the one that we use today, and hexadecimal, which is in base 16. You'll need to convert between them, perform arithmetic in different bases, and solve problems that combine these ideas. By the end of this video, we'll go from the basics all the way to actual ACSL-style problems. So let's start with one question. What does a base actually mean? The number system you already use every day is called decimal, or base 10. But why is it called base 10? Because we have 10 possible digits, ranging from 0 to 9. And once we reach 9, we've run out of digits, so the next number is 10. But here's something important. The number 10 doesn't always mean 10. Its value depends on the base. For example, 10 in base 2 would be equivalent to 2, 10 in base 8 would be equivalent to 8, 10 in base 10 would be equal to 10, and 10 in base 16 would be equal to 16. So what's happening here? Each position in a number represents a power of its base. Let's look at the decimal number 347. We can break this apart as 3 times 100, 4 times 10, and 7 times 1. Or, using powers, it would be 3 times 10 squared, 4 times 10 to the power of 1, and 7 times 10 to the power of 0. So if you add everything together, you get 347. We're using powers of 10 because decimal is base 10. And this exact same idea works in every other number system. The only thing that changes is the base. So let's start with binary. Binary is base 2. That means there are only two possible digits, 0 and 1. There is no 2-digit in binary. So counting in binary looks like this: 0, 1, 10, 11, 100, and so on like this. Next is octal. Octal is base 8, so we have 8 digits ranging from 0 to 7. There is no digit 8. After 7 comes 10. Then we have decimal, which is the normal base 10 number system we're already familiar with. And finally, we have hexadecimal, or hex. Hexadecimal is base 16. But now we have a problem. We normally have 10 normal numerical digits. So how do we represent values from 10 through 15 using one single digit? This is where we use letters. So A is 10, B is 11, and so on until F is 15. Then comes 10, which in base 10 would be equal to 16. You want to memorize A through F because ACSL use hexadecimal constantly. When a number is written, how do we know which base is used? We use something called a subscript. A subscript is a number that represents the base, which is written like this. So this would be read as 45 base 16, or this would be read as 347 base 10. So for base 10, you don't need to add the subscript. If there is no subscript, it is always going to be in base 10, unless it is stated otherwise. So let's start converting numbers. We'll start by converting into decimal. This will show how different bases result in different values, and it's the easiest conversion method to understand. Remember our rule: each position represents a power of the base. Let's start by converting 1101 base 2 to decimal. Because we're in base 2, our place values are powers of 2 instead of 10. Starting from the right, we have 2 to the power of 0 equals 1, 2 to the power of 1 equals 2, 2 to the power of 2 equals 4, and 2 to the power of 3 equals 8. Now we multiply each digit by its respective place value. So 1 times 8 and 1 times 4, 0 times 2, and 1 times 1. That gives us 8 plus 4 plus 0 plus 1, which equals 13. So 1101 base 2 is equal to 13 in base 10. Let's try octal. Convert 175 base 8. Now we're using powers of 8. So we have 1 times 8 squared, 7 times 8 to the power of 1, and 5 times 8 to the power of 0, which becomes 1 times 64 plus 7 times 8 plus 5 times 1. So 64 plus 56 plus 5 equals 125. Therefore, 175 base 8 is equal to 125 base 10. Hex works exactly the same way. So let's say we have 2a base 16. Remember that a equals 10. So 2 times 16 to the power of 1 plus 10 times 16 to the power of 0 becomes 32 plus 10, which gives us 42. So 2a base 16 equals 42 base 10. It's the same process every time. You essentially just multiply each digit with its respective place value and power. Now we're going to do the reverse. Instead of converting to decimal, we're going to convert from decimal to a different base. So suppose we get the question 45 base 10 and we need to convert it into binary. One way we do this is to use powers of 2. Let's list them. 1, 2, 4, 8, 16, 32, and 64. But the largest power that fits inside 45 is 32. So we start with a 1. And then you subtract 32 from 45. So 45 minus 32 is 13. And now we have 13 left. So now we check if the next lowest power fits into 13, which is 16. Can 16 fit inside 13? No. So that position gets a 0. Now we check if 8 fits. And yes, it does. So that place is a 1. And we subtract 8 from 13 to get 5. Now we check, does 4 fit? And yes, it does. So a 1 goes in that spot. And then we subtract 4 from that place. So 5 minus 4 is 1. And does 2 fit in 1? No. So we move on and put a 0 in that place. And does 1 fit? Yes, it does. So we put a 1 there, and our final digits are 1, 0, 1, 1, 0, 1. Therefore, 45 base 10 equals 1, 0, 1, 1, 0, 1 base 2. You can use the same basic idea with powers of 8 or powers of 16. Let's do another example where we convert 10,945 in decimal into hexadecimal. So for this, we're going to use repeated division by 16. So this might be a little bit different than the method we used for binary. So we're going to start by dividing 10,945 by 16. And our answer is 684 with a remainder of 1. And that remainder 1 is going to become our rightmost hexadecimal digit. Now we take 684 and divide by 16 again. Our number becomes 42 with a remainder of 12. But remember, hexadecimal only uses the normal digits 0 through 9. After that we use letters. So since we got a remainder of 12, our next digit is going to be C. Then we take 42 and divide by 16, which is 2 with a remainder of 10. And 10 in hexadecimal is A, so A is our next digit. Finally, 2 divided by 16 is 0 with a remainder of 2. So our last spot is 2. And since our quotient has reached 0, we're done. And we collected our remainders in this order: 1, C, A, and 2. But we don't read it in that order. We actually reverse these numbers to get 2A, C, 1. So our final answer is 10,945 base 10 is equal to 2AC1 base 16. And that's how you convert a decimal number into hexadecimal using repeated division. And you can use repeated division with base 8 as well. and you can use it for binary instead of using the method we used before. So now we know how to convert to and from decimal. But what if you're asked to convert directly from octal to hex? You could convert from octal to decimal, then to hex, but that's way too much math. So there's a faster method: octal to binary to hex. And here's why. Every octal digit corresponds to exactly 3 binary bits, like the list shown below. Hexadecimal works similarly, except every hex digit corresponds to exactly 4 binary bits. For example, here. So let's convert 3676 base 8 into a hex. Convert every octal digit into 3 binary bits, and then we put them all together in the order they are listed. And now we want hexadecimal. So instead of groups of 3, we're going to regroup all the binary bits into groups of 4, starting from the right. And now we convert each group, so 011 becomes 7, 1011 is B, and 110 is E. So 3676 base 8 is equal to 7BE base 16. No decimal conversion is required. This shortcut is definitely worth learning since there are going to be time constraints at the ACSL competition. For this next part, we're going to learn how to add numbers in different bases. So we usually add numbers in base 10, but you can also do the same in different bases. So let's try binary first. So if I wanted to do 1010 plus 1110, and I add them, we would do what we usually do. We would first add these 2 digits. 0 plus 0 is 0, so it goes down here. Then we move on to the next 2 digits. So 1 plus 1 is 2. But remember, we have only 2 digits in binary, 0 and 1. 2 is not an actual digit. So we have to put a 0 here and carry a 1 over. Now we have 1 plus 1. It's the same thing again. We get 2. And 2 is not an actual digit. So we have to put a 0 and carry another 1 over. This time we have 1 plus 1 plus 1. And that is equal to 3. So this time our answer is going to be 1 because 3 minus 2 is 1. Then we finally carry our leftover 1 over here. And our final answer is 11000 base 2. Now let's do an example in base 8. So we have 4572 base 8 plus 6531 base 8. So let's start with these 2 digits just like we did before. 2 plus 1 is 3, so that digit goes here. 7 plus 3 is 10, but 10 is not a valid digit in base 8. So we have to do 10 minus 8, and since that is 2, we put 2 here, and we have to carry over 1. And then we have 1 plus 5, which is 11, but that's also not a valid digit in base 8. So 11 goes over 8 by 3. So 3 goes here, and then we have to carry over 1 again. Then we have 1 plus 4 plus 6, which is 11 again, and that goes over 8 by 3, so we put that here again. Then we carry over our final 1, and we get a final answer of 13323 base 8. Now, let's try subtraction. So just like addition, subtraction is the exact same process as when subtracting in decimal. So here I have 2 base 16 numbers, and we are subtracting them. So it's the same process as regular subtraction, except the base is different, so just keep that in mind. So in the first column, we have A minus E. Remember that A is 10 and E is 14. But 14 is greater than 10, so we can't do 10 minus 14. So we have to carry over 16. In regular base 10 subtraction, we would carry over 10. But since we're in base 16, we carry over 16. And 16 plus 10 is 26. So since we carried over 16, we have 26. And now 26 minus 14 is equal to 12. And 12 is, we can't write 12 here, so instead we have to write C. And now that we carried over 16 from this 8, we have to bring it down to 7. So in this column, we have 7 minus 3, which is 4. Then we move on to the next column, which is B minus 5. And B is equivalent to 11. So 11 minus 5 is equal to 6. And then finally, you just have a standalone 6 with nothing here. So that's just 6 minus 0, which is 6. And our final answer is 664C base 16. Okay, so now we're going to move on to multiplication. So multiplication in different bases, this is the same exact process as you would do in regular multiplication in decimal. So let's start by doing two numbers which are in base 8. And remember, this method works for base 16 and binary as well. Just keep in mind the base when you're doing those. So let's go ahead and start this multiplication. So in regular multiplication, we take the first number at the bottom and multiply with each individual digit. Then we make one row. Then we do the same thing with the other digit and multiply with each digit up here and make a second row. You might not be getting what I'm saying, so let me just show you. It's just like regular multiplication. So 3 times 3 is 9, but 9 is not a valid digit in base 8. So 9 minus 8 is 1, and since 9 goes over 8 by 1, we put a 1 there, and then we carry over a 1 here. Now we have 3 times 5 is 15, but 15 is not a valid digit in base 8 again. So we have to see how much 15 goes over 8 by. It goes over 8 by 7, so we put 7 here. But wait, we have a 1 to add up here, so this will actually become 8. But we can't have 8 here, so we have to put 0, because 8 goes over 8 by 0. So this is actually a 0. Then we carry over 2 instead of 1, because we have to carry over this 1, and we have to carry over the 1 from the overflow of 15. So we have to carry over 2 different ones to get a 2. Then we have 3 times 7 is 21. And 21 goes over 8 by, by 13. But 13 still goes over 8. So 13 goes over 8 by 5. So we put 5 here. But we have a 2 to add, so we just add 2, and it becomes 7. Then we move on to the next row. But just like regular multiplication, we have to put a 0 here first. Now we have 2 times 3 is 6. So 6 goes here. And let me just cross these out. And then we have 2 times 5, which is 10. but 10 goes over 8 again. It goes over 8 by 2, so we put a 2 here and carry over a 1. Then we finally have 2 times 7, which is equal to 14. But 14 goes over 8 by 6. So we would put a 6 here, but there's a 1 to add. So we put a 7 here instead. Finally, just like in regular multiplication, we add the two numbers we got. So 1 plus 0 is 1, 0 plus 6 is 6, 7 plus 2 is 9, but 9 goes over 8 by 1, so we put a 1 here and carry over 1 here. And 1 plus 7 is 8, but we can't have 8, and 8 goes over 8 by 0. So we put a 0 here, and we go over here with a 1 because we have to carry a 1 here now. And our final answer is 10161 base 8. If that all sounds a little confusing, just remember it's just like base 10, except instead of it going over 10, it goes over 8. That's all for computer number systems in ACSL. I will be covering more topics in the intermediate and senior divisions because computer number systems aren't the only topic. And before I end the video, I want to tell you a few things that you should probably memorize for the competition. First, you should know every octal digit in binary, 0 through 7. And second, you should know every hex digit in both decimal and binary, especially the following. And finally, become comfortable with the powers of 2, 8, and 16. The faster you recognize these values, the less math you'll have to do during the time contest. So, that's all. I hope you enjoyed and found this helpful. If you did, please consider liking and subscribing, and I'll see you in the next one.